My name is Pablo from King's. I'm going to be chairing the next session, and we're going to change a bit gears into valves now. Boyce is going to lead us through that journey, and over to you. Thank you.
Thank you. Before I start, I wanted to thank the organizers for the opportunity to give this presentation and to confess that we have not done a lot of uncertainty quantification yet. So this is going to be a talk mostly about modeling and methods related to simulating heart valve dynamics. Before I start, I wanted to acknowledge the people who did most of the work. So I'm going to be talking about some in vitro experimental and computational models of heart valves. A lot of this work has been done by Mike Lee and by Robert Hunt at UNC Chapel Hill. And this has been in collaboration with Larry Scotton. I'll show you some of Larry's equipment a little bit later, as well as Brent Craven and co-workers at the FDA. We're also, I'm going to show some preliminary work on extending this to valve models that are embedded within more realistic descriptions of the whole heart. This is work that's being led by Simone Rossi and by Charles Puls, with a lot of hard work by Margaret Ann Smith, David Wells, and others. So, valves. So these are images of a healthy aortic valve and an aortic valve that has substantial calcific lesions. So the lesions on this valve prevent the valve leaflets from opening fully when the heart contracts. And as a result, the valve presents very substantial resistance to forward flow. And currently, there's no medical treatment for calcific valve disease, or really for any of the really major valve diseases. Really, the only treatment that's available is repair or replacement. So replacement is typically by either a surgical valve. So these are valves that require open heart surgery to implant. This is a mechanical valve. It's a very simple device that has two rigid plates that are actuated along a rigid ring, or a bioprosthetic valve. So bioprosthetic valves are valves that are made out of processed animal tissues. This is an image of a porcine bioprosthetic valve. So the valve is a treated pig aortic valve. The other tissue that's used, and especially in more recent devices that allow for transcatheter delivery, are bovine and porcine pericardial tissues. And so these are examples of valves that are mounted in stents, so you can collapse them down and deploy them using a catheter. And one of the advantages of pericardial tissues compared to pig valves is that you can make valves with much thinner materials. But so valve disease in the United States and in other so-called developed countries is a disease mostly of the elderly or the aged. So in the United States, about 8.5% of the population aged between 65 and 74 has valvular heart disease, and this rises to 13% for the population 75 or older. And so as the population ages, this is going to become a more and more prevalent issue. It's hard to find really good numbers, but there's something like 300,000 heart valve repair or replacement procedures that are performed worldwide right now. And this is projected to be as much as 850,000 a year. So this is a lot of procedures. Increasingly, these procedures are using transcatheter devices for which the surgery is substantially less invasive. But there still are going to be a number of patients that get these kinds of surgical valves. So what we're aiming to do is to develop modeling methodologies, so simulation tools that we can use to develop validated valve models, and with the goal of using these for design, regulation, and questions like that. So we're working towards validation. We have what our first speaker today would probably refer to as a wishy, or not a complete validation. We're working towards validation. Okay. So the methods that we use to do dynamic simulations of valves are a little bit different from traditional computational mechanics methods for doing fluid-solid interaction. So heart valve leaflets are thin, elastic structures. They're immersed in fluid, and they're thin. They essentially move with the flow that they're immersed in, but at the same time they generate forces, and those forces are applied back to the fluid, and they influence the fluid motion. So this view of what the valve is doing motivates the development of what are called immersed methods for fluid structure interaction. I'm going to kind of walk through from more classical methods that are now called immersed boundary methods to methods that handle large deformation nonlinear elasticity. But in order to do that, we need to introduce some concepts. So we're going to be describing an immersed structure, so a structure that's immersed in fluid. We have fluid on the inside, we've got fluid on the outside. And initially, we're going to be thinking of this structure as being a thin elastic interface. So my cartoon here might be a little bit misleading. We're going to be thinking of the case of a thin elastic structure. And it's going to be convenient to describe the dynamics of this coupled fluid structure system using two different coordinate systems. So we're going to use a fixed Eulerian coordinate system, say lowercase x, that has components x1, x2, x3, are going to be fixed physical coordinates in the computational domain. And we're going to describe the dynamics of this coupled system in terms of the Eulerian velocity field, the Eulerian pressure field, and there's going to be an Eulerian body force density that shows up in a minute. We're going to describe the motion of the immersed structure using Lagrangian coordinates. So initially what we're going to do is we're going to attach curvilinear coordinates, say q1, q2, so that a particular value of this curvilinear coordinate q labels a material point for all time. And then chi of q gives us the physical position of material point q at time t. Capital F is the Lagrangian force density. This is going to be a force density that's associated with this interface. And then we're going to keep track of the position of the interface at time t. So the immersed boundary formulation of this fluid structure interaction system is a formulation that was introduced by Charlie Peskin in the 70s in his PhD thesis work, which was in physiology on modeling heart valves. But so what we have is we have the incompressible Navier-Stokes equations augmented by an Eulerian elastic body force. This is a body force density with respect to the three-dimensional coordinate system, x1, x2, x3. We have a Lagrangian force. This is a force density along the interface. This is a force per unit area along the interface. And we're going to convert this Lagrangian force density into an Eulerian force density by integrating it against a delta function. So that's going to give us a singular force that's being applied along this immersed interface. And then the immersed interface is going to move according to the local fluid velocity. So because the fluid is assumed to be a viscous, incompressible fluid, it satisfies the no-slip condition. And the no-slip condition along the interface implies that the interface has to move with the local fluid velocity. So we have a singular force density that's being applied along this interface. And force balance tells us that directly implies that there must be a discontinuity in the pressure across the interface that's proportional to the normal part of that force. And there has to be a discontinuity in the shear stress that's proportional to the tangential part of that force. And so an equivalent formulation of the equations that I just showed you that are written in terms of these integral transforms is to write them in terms of jump conditions that are imposed along the interface. So to discretize these equations, there are a couple of different approaches that you can take. Basically, what we're going to do is we're going to use a Cartesian grid to describe the Eulerian equations. Although you don't have to use a Cartesian grid, you could do something else. We're going to use a body-fitted mesh just for the interface. So this is going to be a Lagrangian mesh for the interface. And then we have to talk a little bit about how to couple these two representations. So if we start from this delta function formulation, we get the classical immersed boundary method. The classical immersed boundary method, what we do is we replace the singular delta function with a regularized version of the delta function. There are a lot of different recipes for constructing delta functions. I'll show you one in just a minute. But essentially what you do is you compute your forces along the interface, and you take those forces and you're going to spread them out onto the nearby Cartesian grid locations, and the weighting that you use is determined by the form of this regularized delta function. And then you solve the Navier-Stokes equations, you get the velocities on the background grid. You have velocities that are not exactly on the interface. And in order to determine the motion of the interface, you're going to sample the background velocities using, in this case, exactly the same regularized delta function kernel that we use to apply the forces. So this is sort of the simplest thing you can do with one of these kinds of methods. This is just an immersed interface in a viscous incompressible fluid. And what you can see in plotting the pressure, you get a sharp discontinuity in the pressure. These interfaces are not required to conform to the background grid. The background grid, in this case, is a locally refined grid that tracks the motion of this interface. But the interface is free to cut through this background grid in sort of an arbitrary way. And in this particular formulation, it's this regularized delta function that allows the geometry to be sort of arbitrary. So briefly, the construction of this regularized delta function on a Cartesian grid, we're going to use a tensor product form where we need to specify the forms of these three component functions. We're going to just take them all to be the same thing. So we have a regularized delta function that's constructed as a concentration of a basic smooth kernel function. And the idea with this particular setup is that as the grid spacing goes to 0, this thing is going to, in some sense, approach a singular function. It's going to be applying a singular force layer to the background grid. So this is just one recipe for constructing regularized delta functions that I like, because I can show you the whole thing just in terms of pictures. So this is a construction that gives a family of kernel functions that's called the cardinal B-spline. So it's related somehow to NURBS. And the idea is that you start off with a function called the window function. So this is a piecewise constant function. If you convolve the window function with itself, you get the hat function. So the exact same function that shows up in low-order finite element methods. If you take the hat function and you convolve it with the window function, you get a bump. As you keep on doing this, you get higher and higher order sort of bump functions. And these things, as you iterate this over and over again, eventually converge to the Gaussian. So in the end, what we're going to do is we're going to compute forces on the interface. We're going to spread them onto the background grid using this regularized delta function. We're going to solve the incompressible Navier-Stokes equations in an approximate sense. We're going to get velocities. We're going to read those velocities to get the motion of the interface. And we're going to encapsulate those force coupling and velocity coupling operators into some compact notation. S is the operator that takes forces from the interface and puts them on the background grid. J is the operator that takes velocities from the background grid and puts them back on the interface. And so you can do fairly complicated things with this. So this is an example of a heart model that was constructed by Charlie Peskin and Dave McQueen. This is a heart failure model. So this is a big dilated heart that's not pumping very well. It's a sort of patient-specific model, but it uses essentially exactly this methodology. You can also say, okay, well, I don't want to regularize my delta functions. I want to avoid regularizing them. So what you can do instead is you can directly discretize these jump conditions. This gives rise to a different method called immersed interface method. The challenge is, well, how do you account for discontinuities in your discretization? And the basic idea is that if you actually know that you have a discontinuity somewhere in your domain, if you have a finite difference approximation to a derivative that spans that discontinuity, and you know the value of the discontinuity, you can bake that in to your approximation and obtain an accurate estimate for derivatives. And so this just requires knowledge of these jump conditions. You get a standard finite difference plus an inhomogeneous term that's like a correction. And the idea with these methods is that really this correction comes directly from knowing what the forces are in the interface. And so in practice, what you have to do is you have to figure out, I've got a finite difference stencil. It crosses my interface. Here's where the interface cut is. I evaluate the forces there. I set up forces on the background grid in a way that's analogous to an immersed boundary method. I have some operator that goes from forces on the background grid and gives me forces, or that goes from forces on the interface and gives me forces on the background grid. And I have a comparable operator that goes from velocities on the background grid to velocities on the interface. So it sort of is doing the job of spreading forces, solving Navier-Stokes equations, interpolating velocities. And And if you look, so this is sort of maybe the simplest thing you can do with this. This is just flow past the cylinder showing you vorticity. And you compare what's happening with an immersed boundary method. With an immersed boundary method, you wind up with some spurious interior flow that is completely eliminated if you go to this immersed interface formulation. So flow past the cylinder is pretty boring. What we're developing this for is for a project with the FDA on modeling flow in the inferior vena cava. If we look at flow in this patient-averaged inferior vena cava model, just down past the confluence of the right and left iliac veins, you get these complicated flow patterns. And if you compare what you get with this immersed interface formulation and what you get with a body-fitted numerical method, in this case implemented in open foam, you get excellent agreement, excellent quantitative agreement between the two methods. And so ultimately what we want to use this for is actually modeling clot trapping in inferior vena cava filters. That's a story for another time. So ultimately we want to be able to handle models in which we don't have just interfaces, but we have immersed bodies or immersed structures, immersed volumetric structures. And so there are more elaborate versions of this formulation that one can construct, but sort of the simplest thing that you can do is you can say, okay, well, I want to use nonlinear mechanics to describe the structural mechanics of this immersed body. So I have a reference configuration that gets mapped into a current configuration using the motion map chi. And in the physical configuration, I want to think about what the stress is, what the Cauchy stress is. And what we're going to say, primarily for computational sort of simplicity, is we're going to assume that there's a fluid-like stress that's defined over the entire physical domain. So there's a fluid-like stress that looks like the stress from a viscous and compressible fluid, and then there are additional solid stresses that are going to be showing up in the solid region. And those solid stresses can come from whatever solid mechanics description you want to use. We are mostly using hyperelastic material responses where you have some energy functional that you can use to determine the, in this case, the first Peel or Kirchhoff stress, but you can use sort of anything that you like to tell you what the solid response is. And so what we do is we then say, okay, I have a common momentum equation. And my common momentum equation is describing the momentum of both the fluid and the solids. This is momentum equation is defined over the entire computational domain. And this is where this formulation is different from a formulation like a arbitrary Lagrange-Eulerian formulation, where you would usually have two different momentum equations, one for the fluid and one for the solid. Here we just have one momentum equation, but there are additional solid forces that are going to show up in the solid region. And those solid forces come from our description of the solid mechanics. So they come from our model of the solid body. One thing that you can hope to take advantage of is the fact that we're solving the incompressible Navier-Stokes equations everywhere in the computational domain makes it seem like it ought to be the case that the structure is automatically incompressible. And that is definitely the case in the continuum equations, but it may not be the case in the discrete equations. So in order to get a formulation that we can actually discretize relatively easily, what we do is we actually introduce a variational statement of this force. So this now looks just like a standard finite element method. We have our force, we integrate it against a test function, we require that to be equal to the double dot product of the Lagrangian stress against the gradient of the test function for all test functions. This is sort of a standard finite element method. And then we're going to replace these singular delta functions with regularized delta functions. And sort of schematically, the way that this works is you kind of compute forces at the nodes of your elements. You sample those forces at quadrature points, and then you spread those forces out from the quadrature points to the background grid. So this, in some sense, decouples the discretization of the structure from the discretization of the background momentum equation. And then you need to perform similar operations to determine the velocities of the structure. So you sample the velocities at these quadrature points using regularized delta functions, and then you solve a L2 projection equation to give you the velocities of the immersed structure. And so you can ask, well, so how well does this work? So this is a verification test. We're using a Mooney-Rivlin material, just a very standard incompressible formulation for the elasticity. We're going to twist it, and we're going to look at how well this thing does in terms of maintaining incompressibility. So you twist it up, and if you just use a standard incompressible elasticity formulation, you get very, very bad results. So you get bad results if you don't worry about whether the structure is incompressible or not. So what we can do is we can add a penalty term. So this is going to start to look more like a method for nearly incompressible elasticity. We add a penalty term that gives us a big energetic penalty if we deviate from incompressibility. Now we're getting much better results in terms of the deformation. We still are losing some volume. So if we finally use a so-called modified deformation gradient, again, a sort of standard technique for nearly incompressible elasticity, we get results that are very good. And if you compare the results to what you get from a benchmark finite element code in terms of the tip displacement as a function of increasing numbers of degrees of freedom, if you do things sort of the right way, you get results that are in excellent agreement with benchmark methods. Okay. If you do things the wrong way, you get results that are very bad. So it's important to do things the right way. I guess that's usually the case. Okay. So valves. I think I'm going to skip over this and go straight to the in vitro model. So we've been working on modeling flow through valves for a while, and we got to the point where we wanted to start to say something about how valid the models are. And in order to do that, the approach that we've been taking is primarily through in vitro experimental model. So the in vitro experimental model that we're using is this pulse duplicator system. So this is a customized version of a commercial pulse duplicator from the vitro. It's a relatively straightforward flow loop. So it has a rigid left atrium. You can put in a mitral valve. You have to put in a mitral valve. It's got a flexible bag. I'll show you a video in just a second that represents the left ventricle. The whole thing is actuated by a computer-controlled piston pump. There's an outflow tract, aortic valve, an ascending aorta that has an idealized aortic root geometry. The whole thing is hooked up to a Windkessel. So it's sort of a classical Windkessel. So it's a compliance and a resistance, and then the whole thing returns. So this is the systems in action. You can see this bag. This is a close-up of the left ventricular bag. So there's fluid that's on the inside of the bag that's coupled in the flow loop, and there's fluid that's on the outside of the bag. I forget to say that. And so the fact that the fluid that's on the outside of the bag is coupled in with this piston pump, and the whole thing is in a rigid chamber, you get you're able to control the contraction of the heart. And this is just a view of a surgical valve in the system. So we've been putting together both models of bileaflet mechanical valves as well as bioprosthetic valves. The two have very different flow dynamics. The flow dynamics of a bileaflet mechanical valve, you have this sort of triple jet. You've got two large jets along the side and a smaller jet along the middle. And the closure of this mechanical valve is really actuated by the adverse pressure gradient. The bioprosthetic valve is very different. So you have one large central jet of flow, and the closure is actually facilitated by the flow dynamics. So there's an eddy, or there's a vortex that gets set up in this sinus, and as the flow decelerates, that eddy applies pressure to the valve leaflet that allows the valve to close essentially without regurgitation. So for bioprosthetic valves, we've been working on both pericardial valves and porcine valves. These are just examples of simulations. Essentially, these are doing the same kinds of things as the movies that I was showing you just a second ago. The main difference with this pericardial bioprosthetic valve is that the geometry is the geometry of a real valve. So it came from CT scan data that we got, that was processed by Brent Craven at the FDA. The porcine valve is at this point using a more idealized geometry. Fiber structure of pericardial and tissue valves are very different. So the pericardial valve is really a manufactured valve. The manufacturer has control over where the fibers go, and they're typically oriented at a 45-degree angle with respect to the circumferential direction. The porcine valve has fibers that span the leaflet like a native valve does. They're data that you can use to fit your constitutive model. So here we're using a version of the Hopsopple-Gasser-Ogden model that includes fiber dispersion. And you can see the effect of that 45-degree angle when you look at the leaflet kinematics. So in particular, what that 45-degree angle is doing is it's causing the valve to twist when it closes. And that twist is designed to allow to ensure that the valve has a good seal at the tip. In contrast, the native valve has structures called the nodes of Orontius, or the nodules. And the idea is that the physiological role of those nodes is to ensure good closure of the valve at the tips. So these are comparisons of experimental and computational results looking at the flow rate through the pericardial bioprosthetic valve. In this case, this video is actually it doesn't correspond to exactly the same operating conditions that are being reported in these summary panels. So this is just sort of an example of what the leaflet kinematics should look like. So the simulation and experiment, are in, I would say, good quantitative agreement in terms of the pressures and the flow rates. They're in sort of reasonable agreement in terms of the leaflet kinematics, although again, these are not exactly the same kinematics as were obtained in the experiment that was used to get the flow properties. This is looking at a comparison for a porcine bioprosthetic valve. And so in this case, we had more data available, more experimental data available. And so you see the confidence intervals about the experimental data. The experimental system is doing a very good job of controlling the flow rate. And we're able to capture the closure transient that shows up in the device by setting up the upstream and downstream models sort of correctly. This is a comparison of the driving and loading pressures, again with these confidence intervals showing you the scatter in the data. The closed valve supports a realistic pressure load without leak. And then this is looking at the leaflet kinematics in some sort of average sense. This is the open area of the valve. So there's a ton of scatter in these data. There's a lot of scatter. The scatter mostly goes away if you look at the power spectrum. So if you do a power analysis, the scattering data is reduced a lot. This solid curve is the computational results. These thinner ones are experimental data. This is in pretty good agreement. I wouldn't say that this is an excellent quantitative agreement, but we get sort of the right trends. The real valve flutters quite a lot. The computational valve does as well. Okay, so I'm running out of time, so I'm going to skip over this. We're doing quantitative flow visualization here in order to start to quantify the agreement in terms of the flow patterns. And so this is just an example of some data that we've acquired using a technique called particle image velocimetry, and have some reasonable qualitative, semi-quantitative agreement in terms of the computational experimental results. So in the computation, we get this big jet that kind of hugs along the left side of the channel. That also shows up if you look, maybe if you have to squint your eyes a little bit at the experimental data. You can do sort of the same things and put together whole heart models. So we've put together models of the heart that include realistic, pretty realistic descriptions of the biomechanics of the valve. So these are still hyperelastic models that have isotropic, or sorry, I shouldn't say that have homogeneous material properties. They're anisotropic. Fiber model of the heart that includes the ventricles as well as the atria. And putting this all together, have some initial simulations of fluid structure interaction. So here, all the motion here is being driven by the fluid structure interaction computation. So none of the motion is prescribed. In this computation, the atria first contract synchronously, then the ventricles contract synchronously. This heart has heart disease, so it has a stenotic aortic valve. It has mitral prolapse. We're working on fixing this stuff. this is a visualization of the flow that's generated in the model. It's slightly higher resolution than what I was showing you a minute ago. So I'll stop there. You can read my conclusions if you like, but thank you very much.
Thank you very much. First question, is the next speaker in the room? Can you start setting up?
Sure.
And the talk is open.
So the choice for the regularization radius, that can affect the condition number for your matrices? Like
It can. Yeah.
Guidelines for the...
Yeah, so it's all very, I would say it's very empirical right now. Yeah. It's definitely the case that smoother kernels are going to have a broader support, are going to be less well conditioned. And in some applications that's okay, in others it's not so good. What we found is that at kind of intermediate Reynolds numbers, you want to use sort of the narrowest kernel that you can get away with. But at really, like in other application regimes, what you want to do is different. So like at kind of nanoscale systems, you might want to do a broader kernel. And I don't know what the story is if you really are in the sort of a really turbulent regime. So here we're in turbulent regime. It's sort of Reynolds number is about 20,000. But if you wanted to go sort of higher than that, you might want to, again, you might need to have more, you might need to satisfy more moments in order to get the right sort of statistics.
You showed the last simulation of flow dynamics. So you say that the simulation was purely fluid driven. Do you have an electromechanical model at all? Or can you elaborate on that?
So it's a fluid structure interaction simulation. So there's a mechanics model. Mechanics model in that particular case is a version of the Guccione model. And then there's an active there's a active tension model. We're using in this case like an additive stress sort of splitting. There's not any electromechanics yet. So the atria are sort of stimulated or activated uniformly, and the ventricles are activated sort of uniformly. There's a finite element mesh for everything. We can, in principle, also do the electrophysiology problem on this. It didn't seem like it was worth doing until we fixed the valvular heart disease that our heart has. It's sort of meant to be a healthy heart, we want to simulate unhealthy hearts at some point also. These data come from a healthy subject, and so we want to try to get it working properly before adding in these additional complexities.
Thank you very much. If no further questions, we're going to clap once more.